Welcome. Today's lesson is implicit differentiation. We'll go over the concept and what it means to be an implicit function to begin with, and then we'll do some examples. So, what is an implicit function? Well, we've talked about this before. We've used this example, but an implicit function is when the y is embedded in the equation, rather than explicitly listed here. Notice, xy equals 1 and y equals 1 over x are the same thing, just multiplied by x, right? They're the same thing. So, if this is a function, that's a function. Now, there are cases where an implicit function actually isn't a function. Think about a circle. It goes like this. For any x value, there might be two values for y. But for any one of those values, here, let me draw a circle. The y is not a function of x, because for any x, we don't know what the y is. But if I look up close, if I take the local linearity approach, right there, ignoring the other side, that's an implicit function. So, how would you find the derivative? Well, back to our case, if we take the derivative of 1 over x, we get minus 1 over x squared. There are many ways to do that. We could either do it with the power rule, that's x to the minus 1. We could do it with the quotient rule. However you do it, that's easy. Over here, it's also easy. It's just not exactly the same. We don't have to solve for y first. We can take the derivative implicitly. Remember that y is not exactly x. It's a function of x. So, y, x. That's a product. If I take the derivative, I can take the derivative of this side and that side. How can we do that? Well, if xy is 1, if xy and 1 are the same thing, their derivatives are the same thing. So the derivative of 1 is 0, and the derivative of xy is going to be something, and those derivatives will be the same. What is that something? Well, this is the product, x times y. So the product, we use the product rule. The derivative of x, which is 1, times y, plus the derivative of y times x. Notice, x and y, as I said, don't behave exactly the same. Y is a function, so when you take its derivative, it stays with the y prime. X is x, it's the variable, so when you take its derivative, it's 1. What do we do next? We solve for y prime. I brought all the y primes over to one side, divided, I get minus y over x. And that looks different than we did in the previous case, but it is algebraically the same. Here's an example point, 2 1/2. If I plug that in here, I get minus 1/4. If I put 2 and 1/2 in here, so I also get minus 1/4. The algebra is slightly different, but the numbers are the same. And actually, if you multiply the top and bottom by x, you get x squared at the bottom. The top, because of this relationship, is minus 1. It actually does simplify as the same thing. So this is an example where you could solve for y directly. If you solve for y directly, it should work the same. And if you can solve for y directly, it's probably easier to take the derivative anyway. But if you can't, implicit differentiation works kind of like this. Let's try an example. Here's an example. Work it through. I'll give you a couple seconds. Okay. Maybe you got through it. Maybe you got stumped. Maybe you kind of got stalled or messed up somewhere. Let's work through and see what you did. This side is that side, so the derivative of the left is the same as the derivative of the right. The derivative of the right is easy. 3 is a constant. Its derivative will have to be 0. The derivative of the left is not so easy, but it's something minus something. So the derivative is the derivative of the first something minus the derivative of the second something. So, x squared times y is a product. When we take the derivative, we get a product rule. The derivative of x squared is 2x, the derivative, then times y, not times the derivative of y. Remember, product rule is f prime g plus g prime f. It's not f prime times g prime ever. But then we have a plus sign, the derivative of the second one, which is y prime, times the first one. Now, what about over here? The derivative of the first one is y squared. What is the derivative of y squared? Well, this is trickier. So let me write that up here. What is the derivative of y squared? Well, again, y is a function. So this is a function squared. It's a g of x squared. That's a chain rule. So the chain rule says, bring the 2 down, subtract 1 power from y. I could put a 1 here, but then it would look like a prime, so I'm not gonna. But I'm not done because y is a function. I also have to go times y prime. This is how y is different than x. Take the derivative like you would otherwise, but multiply by y prime. That'll work for every piece. When you have a y there, take the derivative like you would for x, but instead of finishing then, just multiply by y prime. So it's 2y, and then we multiply by y prime, times x. That's this derivative times that, plus the derivative of x times the first one. Now that's messy, so I'm going to rewrite these. I'm going to get 2xy plus x squared y prime minus 2xy y prime. I like to write my x's before my y's. And then plus y squared equals 0. And then, hopefully, you see the mistake. I made a little mistake. I did it on purpose, actually. But what is the mistake? The mistake is that minus all of this means this is minus. Be careful when you take these derivatives. There's so many things going on, it's easy to forget. I put a parenthesis here for a reason, because when I took the derivative of this, I knew there'd be two pieces, and I wanted to subtract them both right here. So, the next step is to keep all the y primes on one side. Here's a y prime term, here's a y prime term. Keep them here. I have an x squared term minus 2xy. Here, bring the other two over. So I get a y squared minus 2xy. Divide out, I get y prime equals y squared minus 2xy over x squared minus 2xy. It looks very symmetric, and that seems a little strange. But this is very symmetric, so it seems reasonable. Hopefully it makes some sense. Let's apply that sense to one more problem. Find the tangent line to this equation at this point. Normally, when you find a tangent line, I say when x equals some value. I'm actually telling you more than x. I'm telling you x and y. Because sometimes there may be more than one y value, so you really have to know what the y is. If y is an implicit function, you can't just plug x in and go, oh, and then that's what y is. So we usually have x's and y values if we're going to find it at a specific point. Try it out. Okay, hopefully it made sense, but let's do it. I'm going to take the derivatives. The derivative of y cubed, remembering what we just did, it's going to be 3y squared, just like for x's, but then times y prime, minus, now the derivative of xy, hopefully you realize that's a product, so I need a parentheses. And then going ahead, the derivative of 4 will be 0. So, derivative of x times y plus the derivative of y times x. That minus sign means we have to distribute it. So I get 3y squared y prime minus y minus x y prime equals 0. Now I could solve for y prime here, but I'm only interested at what happens at this one point. So now I'm going to plug x's and y's in. So if I plug 2 in for y, 2 times 2 times 3, that's 12 y prime minus 2 minus 2 y prime equals 0, or 10 y prime equals 2, or y prime is 1/5. Let me solve for that now. That's the derivative, that's the slope. So y equals 1/5 x plus box. And I know that the x and y are 2 and 2 respectively. So 2 is 2/5 plus what? Well, to make that work, I need 10/5 over here, so I need 7 more fifths. So the final answer is y equals 1/5 x plus 7/5. There's our tangent line. Now I want to make a comment here. I plugged the values in. I could have solved for y prime and then plugged them in, but I decided to plug them in before that. That's okay. But then you might be asking, well, why not just plug the values in here before I take the derivative? Because that'd be so much easier. The problem is if x and y are things that move around, we have to keep them as x's and y's until we take the derivative. The derivative takes advantage of the fact that they're moving around and gives us a formula. Once that's happened, Everything else is algebra. Once we've taken that derivative, we no longer have to worry about x's and y's in particular. Then we can plug them in anytime thereafter. Try some of these out. Hopefully you'll find they're not as bad as they look. Until next time, this is Dr. Jed.